So let's start with another counting problem. Let's prove that for any three integers n, m, and k, n plus m choose k is equal to the sum, as a ranges from 0 to k, of the product of binomial coefficients n choose a, m choose k minus a. So of course this is kind of a hard problem. You look at one of the two sides and figure out the counting problem you might have started with. We know binomial coefficients, and we know many interpretations, either in terms of choosing subsets or lattice paths. If this were an n or an m, I would be looking at this as a lattice path, but because this integer might be different, I might be tempted to look at subsets. So the left-hand side looks like the number of subsets of the integers 1 through n plus m of size k. Well, when would you be considering some sort of problem involving n plus m? Maybe you're thinking that I'm picking a set of k math majors from a set of n plus m math majors, n of which tend to live in Edinburgh, and m of which live over by Brownsville, since we have two campuses, right? So that gives you a counting problem, a real-world counting problem. There's a number of ways to pick k math majors, where n live on one campus and m live on the other. Well, how else could you solve that problem? If you're taking k math majors from Edinburgh and Brownsville, well, you have to take some number from Edinburgh, so let n be the students in Edinburgh. You know, any such subset has to have some a from Edinburgh and some k minus a from Brownsville. And so that's the two steps. Another way you could form these committees is by first choosing some students from Edinburgh and n choose a many ways, and then choosing the rest from Brownsville and m choose k minus a many ways. And since a is allowed to vary, you actually have a summation. More formally, the idea is that you've got case 1. You've decided that the size of S intersect n is going to be a size 0, or I should say case 0. Then here you've got n choose 0 times m choose k. Everybody's in Brownsville. In general, in case I, any subset, hold on. Let's consider the following counting problem. For any positive integers n, m, and k, we claim that n plus m choose k is equal to the sum n choose a, m choose k minus a, as a ranges from 0 up to k. So we see the left-hand side corresponds to choosing a subset of the integers 1 through n plus m of size k, or something with lattice paths, but since k, n, and m are very different, I don't see how to use lattice paths in this case. Well, this looks like you're picking k people from two different groups of people. To put it in terms of what we're used to, let's say this is a problem of choosing k math majors from n math majors who live in Brownsville and m math majors who live in Edinburgh. How many ways could you solve this problem? On one hand, you're just picking k students from a group of n plus m, and we're not requiring a certain number to live on either campus, and so this is the correct answer. On the other hand, let's consider solving the problem by first deciding how many we're going to take from Brownsville. So case A, we take a students from Brownsville, where a is some number between 0 and k. Well, how many ways can you pick the students from Brownsville that are going to go in your set of k students? Well, you choose this intersection and n choose a many ways, because there are n students in Brownsville and you're choosing a of them to be on your committee or team. On the other hand, the number of ways you can choose the students in Edinburgh, well, if they're on the committee and they're not in Brownsville, they have to be in Edinburgh, so this must contain the remaining k minus a students. Why? Because you wanted k students in total, and you've decided a of them are going to live in Brownsville. And so how many ways can you form your team so that k minus a students from Edinburgh are on the team? Well, in m, choose k minus a many ways. M is the number of students total students in Edinburgh. And so we see the set is given by first choosing the people in Brownsville and then choosing the people in Edinburgh. And since this is a sequence of options, we see that we should use the multiplication principle. these choices were independent. And so we have n choose A times m choose k minus A many teams of size k, where A of the students are chosen from the Brownsville students. So that solves the counting problem, where we fix the number of students from our team who are in Brownsville. We notice, of course, these cases, as A varies from 0 up to k, are entirely disjoint. If your team has 0 students from Brownsville, then it can't have 2 students from Brownsville. And so that means we're taking an OR. You have to first specify which of these cases you want to be in. Therefore, by the addition principle, our counting problem is a sum. So the total number is the sum over all A going from 0 to k, this product of binomial coefficients. And so that's a second way of solving our problem. Therefore, we've solved our problem 2 different ways. And since, 5 is always equal to 5, or whatever the number happens to be, these 2 numbers always have to be the same. Therefore, we have proven this identity involving binomial coefficients using combinatorial arguments. Here we mention a very important example of double counting that pops up a lot in combinatorics called the rule of bijections. It says if you have a function between 2 sets, finite sets A and B, and that function is a bijection, or is 1 to 1 and onto, then the number of elements in A is equal to the number of elements in B. And here's proof by picture. Take each element in A, it maps to something in B. Moreover, the thing it maps to in B is unique. It is the only thing that maps to that element. And so if you take another point in A, it's going to have to map to something else. And so on and so forth, until you run out of all the elements of A. And so that tells you that the size of A is at most the size of B. That's using the fact that the function is injective. Distinct inputs have to get sent to distinct outputs. On the other hand, the function is surjective, so there is nothing in B that doesn't have a preimage. Every point in B has to have a preimage. So we've actually managed to cover every element in B with one of these arrows. And so because you're surjective, B is at most the size of A. And so actually they have the same size. In fact, this pops up so much in combinatorics that we sometimes refer to this as a one-to-one correspondence instead of a bijection. And so I once saw a talk by Doran Zeilberger, and his way to state this is that on Noah's Ark, if you wanted to prove that there were an even number of animals, one way is to give a bijection between the male animals and the female animals. How do you know such a bijection exists? Because according to the book of Genesis, every male had a female partner. So every animal had its mate, and so that gives you the bijection. Every animal had a unique female to mate with. And therefore, that gives you this kind of formula. We'll do a few bijections in this course, but not many. In general, we use this when we have 2 counting problems that appear to have the same answer, but we don't have a formula for either. Or when we have a new counting problem and it turns out seems to have a familiar formula, then we just show a bijection to something that's previously been solved in the literature and call it a day. So here's our first example of identity I want to prove using bijection. N choose k equals n choose n minus k. Admittedly, if you plug in the formulas for binomial coefficients, this is obvious. But that's an algebraic argument. There should be a combinatorial explanation using the definition of binomial coefficients. This is the number of subsets of size k of a set of size n. This is a number of subsets of size n minus k of size n. Well, one way to do this, that's the subset notion. I'll use the bit string interpretation. So this is the number of n bit strings with exactly k ones. Well, we want to, and this would be the number of n bit strings with exactly n minus k ones. Well, how could we actually match these things up? Well, given a sequence a1 through an, a bit string, we'll define f to be a new bit string. Basically, it's swapping the roles of 1 and 0, where ai is 0, bi is 1. Where ai is 1, bi is 0. So for instance, it sends the sequence 10110 to the sequence 01001. And so it sends a bit string of length n with exactly k ones to a bit string of length n with exactly n minus k ones. Why is that? Because there are n minus k zeros over here, and the zeros become ones. And it's not too hard to show that this is a bijection. Given any string over here, replace the ones and the zeros, and you now have something in the preimage that maps to it. And vice versa, if any two strings map to the same element under this map, then the ith coordinates over here must be equal, which means the ith coordinates had to have been equal to begin with. And so it is also injective. And so it is a bijection, and therefore, by the rule of bijections, these two numbers are the same. As another example of a bijective proof using binomial coefficients, if you use the binomial theorem and you set x equal to -1 and y equal to 1, on one hand you get 0. Here, of course, I should assume that n is positive, because that's 0 to the n. On the other hand, by the binomial theorem, it expands as this sum of -1 to the k and choose k. So this alternating sum is 0. Some of the terms are negative, some of the terms are positive. Move the negative terms to the other side. The negative terms correspond to when k is even. So if you sum over all k even, the binomial coefficients n choose k, you get, on the other side, the cases where this was positive, when k was, or wait, scratch that, evens when this is 1. All right, though. But either way, on the other side, you get the odd ones. So this is the size of the number of subsets of even size. This is the number of subsets of odd size. And from the binomial theorem, we see that these two numbers have to agree. A corollary of that fact is that means that exactly half the subsets of exactly half of the subsets have even size and half have odd size, and so that means both these numbers are actually equal to 2 to the n minus 1. So that part is not a double counting argument, and it actually gives a simpler proof of one of your homework problems. This calculation is a lot easier to calculate. Well, how do we prove it? Well, we're going to consider the numbers 1 through n, and we're going to be looking at even subsets of this set and odd subsets of this set. Well, remember n is certainly a number in here. We're going to define a bijection between the even size subsets and the odd size subsets as follows. Given a subset of even size, we're going to define f of s as follows. We take away, if n is an element of s, we remove it. Otherwise, when n is not an element of s, we add it. So for instance, let's say n in this case is 17. Then since 17 is not in this set, we add it. On the other hand, if 17 was already in the set, we remove it. And so you see, since you're adding exactly one element to an even size subset, you're going to get an odd size subset. On the other hand, if you're removing exactly one element from an even size subset, you're going to get an odd size subset. So we do see, in fact, that these two sets are in O. So this actually is the correct codomain for this operation. It's also not too hard to show it's a bijection. The inverse, by giving it formula for the inverse is actually defined the same way. If you take a set of odd size, if it has n in it, remove it, you now get a subset of even size without n. And likewise, if n wasn't present, you add it in. And so you see it's a bijection because you add n and then remove it, or you remove n and then add it. The other way is to just prove surjectivity and injectivity. But either case, you can check that this is a bijection, and so the number of subsets of even size is equal to the number of subsets of odd size. And this gives you a direct proof of this fact, whereas if you use this theorem to do it, well, it also counts as an argument, but, you know, it's not clear why this should be true. using the binomial theorem, and this direct bijection gives you an exact reason why it should be true.